is Dan Boneh from Stanford University, and he's going to be talking about algebraic multilinear and open questions.
Great, thanks, Alice. So apparently I didn't quite follow instructions. I gave a talk at the Simons Institute a few weeks ago, and Alice wanted me to give the same talk here, but somehow that's not what I did. So be it. But then once I saw that this is more, I kind of prepared more of a talk for without too much overview. But then as I saw Alice and Daniela's talk, I kind of merged slides in for my previous talk. So there's a little bit more background now. So we'll see how it goes. And there's a whiteboard that I can always use indeed. So this talk really is about a plea for help. So so we're in the crypto community. We're working on this important topic of multilinear maps. Right now there's really kind of one path towards these multilinear maps. Maybe one path that bifurcates into a couple of paths, but it's kind of a high-level approach. And I am absolutely convinced that there's yet another completely unexplored direction towards building multilinear maps. And I want to tell you a little bit about what we've done looking in that direction, although it's all failed so far. So no success, and really we're stuck, and we need your help, the mathematicians, although the cryptographers should also work on this, in kind of getting us unstuck. But as I said before, I added a few more background slides. So before I get to the actual hard open question, I'll do a little bit of background. All right. So as I like to start always, the world of public key crypto was invented in 1976. I learned in talks to mathematicians that I shouldn't just write 76. I should always write 1976 because mathematicians always ask which century. For computer scientists, it's pretty much obvious. So in 1976, our field was kind of created. That's right. And so, the field was created by Diffie-Hellman, of course, with the realization that there's a group which turns out to be really useful for crypto. In particular, what the notation I'll use, I'll call this group G. It has prime order P. I'll use little g to always denote the generator of this group. And here, when we talk about this group, we always kind of assume an implicit group generation algorithm. The group generation algorithm takes a security parameter lambda, which indicates how hard the problem is, which I'll explain in just a second. And what this group generation algorithm does is it outputs the prime, which is the order of the group, the generator for the group, and an algorithm for carrying out the group operation. So the properties of the group that Diffie-Hellman identified, I'm sure you know what they are, but let me just kind of write out what the properties are. I want to be very explicit here. So the properties are, first of all, the group operation is efficient. So if I give you two elements in this group, then there is an efficient algorithm that will produce the representation of their product. The second property is that the discrete log problem needs to be difficult. So again, I assume everybody knows what the discrete log is. Basically, given there's no efficient algorithm, then given g and g to the x will output x with non-negligible probability. So the discrete log problem is one. And the third property is that every element in this group actually has some sort of a canonical representation. So why is it important that there's a canonical representation? Because then that allows us to do quick, fast equality checks, right? And again, you all know what groups have been used in crypto so far. Basically, the finite, the multiplicative group of a finite field, or maybe the group of points of an elliptic curve. Those are groups that seem to satisfy these kind of properties, right? So efficient group operations, hard discrete log, and every element. It doesn't have a unique representation, right? You can think of projective coordinates here. Elements could have many, many representations, but there is it's very easy to canonicalize and test equality. Yeah, actually in crypto, we definitely like groups that have prime order P. Yeah, so I'm going to assume throughout the talk that all our groups always have prime order P. It just simplifies things. Yeah, okay. Excellent. Good catch. So what I should say here is subgroup of Z over Z mod P, subgroup that has prime order. Excellent catch. Yes, thank you. And in fact, here we also try to focus on elliptic curves that also have prime order. Now, it actually turns out that for a lot of applications, we don't actually need the prime order. It just makes everything a lot simpler. So I'm just going to assume all the groups have prime order. And as we know, this kind of allows a lot of applications: key exchange, public key encryption, digital signatures, and so on and so forth. So this is kind of the state of crypto until the late 90s. The next thing that happens, the next structure that was introduced is sort of these bilinear maps. So here, again, I'll just quickly review what these bilinear maps are, and then we'll talk about them in a bit more detail. So I'm going to use this funny notation for them. I hope I'm consistent here because I pulled slides from different areas. But I'm going to use three groups. I'm going to call them G2, G3, and G6. They're groups of prime order P. It will become clear to you why I use these funny indices once we start talking about multilinear maps. As usual, we have a group generation algorithm that, given a security parameter, what it will do is, again, it will generate the order of these groups. All these groups have the same order. They're all order P. G2 and G3 are generators. G2 is a generator of G2. G3 is a generator of G3. There is a group operation algorithm that will act inside these groups. So given elements in G2, it will multiply them, and produce an element in G2. Given elements in G3, it will multiply them, produce an element in G3, and the same for G6. We want this discrete log to be hard in all these groups. And again, for now, we'll say that all these groups have a canonical representation. So equality is trivial. Every element has a unique representation. And the new property is this group generation algorithm also outputs a pairing algorithm. Yeah, so this is an algorithm. And the pairing algorithm, what it does is just what you'd expect a bilinear map to do. This is the property that's sufficient for bilinearity because I'm assuming the groups have prime order. So this implies bilinearity. And again, this map has to be efficiently computable and it better be non-degenerate. It shouldn't map everything to 1, otherwise it's not interesting. Okay, so these are bilinear groups. I imagine many of you have seen these before. And in fact, they enable many kind of advanced applications in crypto. And so I wanted to say, before jumping to multilinear maps, which would be kind of the next step beyond these bilinear groups, I wanted to just quickly talk a little bit about where these bilinear groups come from and what they're actually good for. And so the way they're constructed is typically by using pairings on elliptic curves. In particular, I use the Weil pairing. The Weil pairing is actually typically not what's implemented. The Tate pairing is what's typically used. But again, to keep things simple, let's just talk about the Weil pairing. And so here what we do is we say, well, let's look at an elliptic curve over some finite field, so E over F, E, F, Q. We'll look at the points over the base field, and we'll call that the group G3. And then we're going to go over to some extension, and still we're going to look, so EFQ, I'm going to assume the size of EFQ has, this group has P points in it. This is a group of order P. And then we're going to go to an extension, and we're going to look at all the points of order P on this curve. So what this funny notation here means is all points of order P all points of order P on this curve, let's assume they live in this extension of degree alpha. Okay, so we know that this forms a 2x2 structure, so it's a two-dimensional structure. Sorry. It forms a two-dimensional structure. G3 again is the base group. In this two-dimensional structure, we also choose one direction. We're going to choose one line, and we're going to call that the group G2. This is again a group of order P. This particular line, in principle, could be arbitrary. Could be any subgroup of order P in this two-dimensional space, but it turns out there's a natural group to choose. I'll just say it, G2 typically is a group of points that has trace 0. And it doesn't matter. If you don't know what that is, it doesn't really matter. Just know that there is some group of order P that lives, where the points live in the extension. Okay, so now we have our group G2 and G3, and that actually defines, there's a pairing defined on this structure that maps G2 times G3 to basically to this other group, G6. Okay, so one way to think of this pairing is as follows. I give you points P1 and P2. Yeah, so P2 generates the group. They generate their appropriate groups. Now, if I give you 2 points Q1 and Q2 arbitrarily in this two-dimensional structure, okay, these are all points of order P on this curve. Really, you can think of the pairing as sort of a determinant. So what do I mean by that? What I mean is you can take arbitrary points Q1 and Q2. You can express them as linear combinations of P1 and P2. And now you can compute a pairing. Basically, you can define the pairing as as basically some group element G6 raised to this determinant of A, B, C, D. Now, actually, I should be clear. I wasn't clear before. Just this group G6, this generator G6, this is a generator of basically of the finite field. So FQ to the alpha star. So G6. This slide is not very good. So G6 lives in FQ to the alpha star. And what the pairing does is it takes 2 points, Q1 and Q2, and maps them over to the finite field, FQ to the alpha. So far, so good? Any questions on this? Yes. I'm actually doing, normally we would only allow Q1 and Q2 to live inside of these two groups. Yeah, in which case this becomes really simple because it's just the determinant of a diagonal matrix. Yes, but let's be a little bit more general and allow the pairing for just a minute to actually operate in the entire two-dimensional space, in which case the pairing would just be defined as a unity. Okay, and it just basically we take sort of a root of unity, this would be a root of unity, and we raise it to the power of this determinant. So just keep that in mind, that you can literally think of the pairing as a 2x2 determinant. But you're absolutely right. Usually we will just worry about these two groups, and we'll just pair elements in these two groups. Okay, so what do these pairing allow us to do? Well, so what we can do with them, for example, again, so let me go back to the original slide. So we have a pairing now that pairs elements in two groups and map them to some third group. So in the case of elliptic curves, G2 and G3 are subgroups of the elliptic curve, and G6 lives in the finite field. That's where we are. Okay. So what does it allow us to do? So things we can do with these pairings, like why are they interesting from a cryptographic point of view? Well, things that we can do with them are, for example, take two matrices, A and B. Yes, these are matrices over FP. Now you can literally think of putting these matrices in the exponent. What I mean by that is G2 to the matrix A means literally take the matrix where each component of the matrix is that element in the original matrix A raised to the power of G2, or G2 to that power. Yes, so G2 to the A, B, C, D would literally be the matrix G2 to the power of A, G2 to the power of B, G2 to the power of C, G2 to the power of D. Okay, that's what this notation means. So what the pairing allows us to do essentially is do kind of matrix multiplications in the exponents. Okay, so one bilinear map allows us to do multiplications even though the elements are not given to us, the matrices are not given to us in the clear. They're given to us only as exponents, and still we can multiply them. Now the interesting thing, of course, is we can multiply two matrices, but we can't multiply any more. Yeah, and that's exactly where why we would want to go beyond bilinearity, right? We would want to actually be able to multiply more than just two matrices, and we'll see where that comes up in just a minute. Okay, fine. And more generally, we can basically compute quadratic polynomials in the exponents, but no more than quadratic, right? Bilinearity means we can do quadratics, and that's it. All right, so I was going to jump now and talk about constructions for multilinear maps, but let me just kind of, if you haven't seen, I guess for the mathematicians in the audience, if you haven't seen pairings in crypto before, let me just give you just one example of why pairings are so useful in crypto, and some of the properties that come from this application. This is the simplest applications of pairings to crypto. So let me do that very quickly. So this is an application to signatures. So in case you want to teach this in class or so, this is a really simple application. So let me briefly remind you what a digital signature system is. So a digital signature system is one where you can generate a public key and a secret key for yourself. So the public key you advertise to the world, the secret key you keep to yourself. You can use the secret key to sign messages, and then you can verify signatures using the public key. But basically, anyone who has the public key can verify a signature on a message M. Okay, so that's what a digital signature system is, and let's not worry about security just yet. So I hope everybody here has seen this. Yes, please let me know. Raise your hand if you haven't seen digital signatures before. Oh, very good. All right, so let's see how do we use pairings to do digital signatures? Well, it turns out there's a really, really easy construction. And so let me explain to you how it works. So what we'll do is we'll take our two groups. Well, okay, G1 and G2, I guess they're called here. Sorry, the slides are a little inconsistent because I pulled these at the last minute. Okay, so anyhow, so we have G1 is a generator of the group capital G1, and we have G2 is a generator of this vertical group here. We'll set the public key to be just G2 to the alpha for some secret value alpha. Okay, that's it. And we publish this public key. So alpha is going to be our secret key, and G2 to the alpha is going to be the public key. Right, so far so good. Now, in addition, we're going to choose some hash function, and how we choose it, I'm not going to specify it. We'll choose some hash function that hashes elements, basically hashes arbitrary strings into the group G1. So that means essentially you have to have a way to map strings into points on the elliptic curve. Generally, this is going to have to be some sort of a, well, we're going to treat this as a random oracle, which means we're going to treat this as some sort of a randomized function. But for now, let's just pretend it's an arbitrary hash function and not worry about how it's actually implemented. Okay, so what do we do? So basically, again, as I said, the key generator outputs the two generators G1 and G2. The public key is just G to the alpha. The secret key is alpha. Now, the signing algorithm is trivial. Really, really simple. If I want to sign a message M, all I do is I hash the message M onto the group G1, and the signature is just going to be H of M to the alpha. That's it. Really, really, really simple signature algorithm. And the question is, how do we verify these signatures? And the way we verify is basically using the pairing. So if you just think about this for 1 second, you'll see that if the signature is valid, I can very easily simply pair the hash of the message with the public key and compare that to the pairing of the signature and G2. And let's just to convince yourself that this will verify correctly for valid signatures, I'll just plug in the values. Yeah, so you can see that if I put the public key was just G2 to the alpha, so if I plug in G to the alpha here, by bilinearity, alpha will come out of the parentheses, and it can come back into the parentheses on H of M, and H of M to the alpha is sigma. Okay, so you can verify equality. Yes? Does this make sense? Everybody agrees? Okay, so this is like really the easiest application of pairings to crypto. You get a very, very simple signature system. And the question is, why is this secure? So again, I'm not going to talk too much about security here. I'll just tell you this is secure under a variant of the computational Diffie-Hellman assumption. I wrote it over here in the random oracle model. So assuming the hash function H is a random oracle. And there's actually a lot of work on building pairing-based signature schemes that are secure without random oracles. And there are many, many, many constructions for these signature schemes secure without random oracles. But I'm just going to talk about this signature scheme for just a few more seconds, and then we'll move on to multilinear maps. So again, if you want to teach an application of pairings, this is the easiest application to give. And already, even though this is such a simple signature scheme, already it has properties that we have not seen before. So let me give you some examples. First of all, the signature is really, really short. So let me explain what I mean by this. So suppose I want a signature scheme where the best attack on the signature scheme runs in time 2 to the lambda. So lambda is our security parameter, right? And we want the best possible attack. So what I mean by that is that an attacker can ask for signatures on any messages of his choice. And then his goal is to forge the signature on some other message. We'd like that to take time 2 to the lambda. And the question is, what's the shortest possible signature scheme that we can give under these constraints? So again, the best attack should take time 2 to the lambda. So it turns out RSA is actually not such a good algorithm in this case, because factoring at the end of the day is there are sub-exponential attacks on factoring. So generally you have to use relatively large moduli, and that causes the signature size in RSA to be quite large. So in practice, you can see the signatures are quite big. There's another algorithm called DSA, elliptic curve variant of DSA. Here the size of the signature would be 4 lambda. There's an improvement due to Schnorr called 3 lambda. And it turns out using pairings, so before we could never go below 3 lambda. This was like the best we could do. There was nothing before pairings that breaks this barrier. Using pairings, it turns out actually we can actually go down to 2 lambda. And let me ask you, why is it that we need 2 lambda security? So why is it the signature scheme has to be 2 lambda? Why can't we go below 2 lambda with these pairings? What would go wrong? So let's think for just 1 second about what is the length of the signature here. The signature, if you remember, the signature is just an element on the elliptic curve, yeah, in the ground field of the elliptic curve, just a point on the curve. So again, a signature is a point on the curve. Why can't the signature? And what I'm telling you is that if I want a signature scheme whose security is going to take time 2 to the lambda to break, and I'm saying that we cannot use curves where the representation of points on the curves is less than 2 lambda. So why is that the case? Is what? Polar draw. Yeah, exactly. Thank you. Yes, Leo. Thanks. So exactly, if you have a group where elements in the group are 2 lambda bits, that means the group size, right, is going to be right 2 to the 2 lambda. Using polar draw, essentially, you can compute discrete log in time 2 to the lambda. So if you want security 2 to the lambda, your group size has to be at least 2 to the 2 lambda, and that forces the signature size to be 2 lambda bits. Is that clear? Yes? No?
Or you could just choose random messages and after you put it on that hand,
Yeah, that's another way to say polar draw. That actually not quite. There's no row here, but yeah, that's another. I guess there would be more baby step, giant step like method. Yeah, that's another way to say it. Exactly. If you, right. Right. So the question. Wait. What? So you're saying choose random messages. If your signature length was less than 2 lambda, then you might have a collision. Well, okay. So not necessarily, but it turns out for this it would. For BLS it would be true. And anyhow, you cannot go below 2 lambda bits with this. But there is this question of whether we can do better than 2 lambda bits. Yeah. So it turns out actually that birthday attack actually doesn't quite apply. And in fact, there is a result that says using actually, well, yeah, so using big hammers in crypto, using obfuscation, there's a result to Amit and Brent Waters that actually shows that you actually can get shorter signatures that are only lambda bits. But unfortunately, those are pretty big hammers, and we can't quite implement those today. And so there is a really, really nice open problem that would be nice to solve, which is like, is there a way to actually go below this 2 lambda bit barrier in a way that actually, we actually can implement an experiment with? We know that this exists, yes, because of the big hammers. We know it exists. The question is, can we actually come up with such a signature scheme that we can implement? So for example, is there a way to use, I don't know, LWE, lattices, to come up with shorter signatures? So far, signatures using lattices seem to be quite large, somewhat longer than this. So maybe not, but lattices have surprised us before, so you never know. Maybe there's a way to come up with a short signature scheme using, again, the multilinear maps that I'll talk about later on. That, again, would be really nice. I give you, let's say I want a 128-bit signature, so security is 2 to the 128. I give you a 128-way multilinear map. Can you construct a signature that's only 128 bits? We don't know. That's an open problem. So again, this would be quite interesting and would be nice to solve. So one property immediately that you get from this very short signature scheme, very simple signature scheme, it's already shorter than anything we had before, although maybe we can improve that in the future. Another property that it has, again, just showing you why bilinear maps are so useful, is all of a sudden it has this property that we've never seen before, called signature aggregation. This is in a paper with Craig that does the following. Basically, what signature aggregation allows you to do is allows you to take a bunch of signatures from many different people and kind of compress them into just a single signature that, as the size of sigma star, is exactly the same size as just sigma 1. Yeah, so you can take a lot of signatures and compress them into one. And essentially, this one simple aggregate signature actually convinces the verifier that all the messages were properly signed by the given public keys. Yeah, so it's really quite remarkable that you can take like 1 million signatures, compress them very easily into just one signature, and that one signature will convince you that all 1 million messages were properly signed. So let me just give you one example of where this comes up. There's something called certificate chains. Maybe you have heard of them or maybe not. These are things that are actually used quite a bit on the web all the time. Today, certificate chains, basically, they all have to have multiple signatures embedded in them. Well, if everybody was using pairings on elliptic curves, you can actually take all these signatures and compress them into one. Yeah, so that would shorten these certificate chains. Yeah, so that's kind of a nice application for this. So how do we aggregate these signatures? Let me just very quickly show you how it's done, very simply. So again, remember, a signature is simply the hash of a message raised to a certain power. Yes? So I give you 1,000,000 of these signatures on a bunch of different messages. The signature aggregation mechanism is really easy. All you do, fun problems. All you do, this is an arrow. Yeah, there's a left arrow there. Okay. All you do is basically you take all the signatures that you were given, you multiply them together, and that's the compressed signature. Okay, so very simple aggregation mechanism. And again, someone should ask me, well, how do we verify this aggregates? Thanks, Chris. That was a really good question. The way we verify the aggregate basically is, again, using the map. Lost the apple. Okay, there are problems with the slides here, but so be it. So what we do is we basically just do this comparison here, right? So we take the product of all the messages in the public keys and compare that to a pairing of the aggregates and the generator G. Yeah, that was a sigma. I don't. Sorry. This is what happens when I pull slides in at the last minute. This is to comply with your suggestions, Alice. What? There we go. There we go. Okay, and you can see again if you just do the expansion, you can kind of follow through with the bilinearity properties. Basically, what happens is, by bilinearity, this alpha I can jump from the right to the left. Yeah, so that's what happened here. And once it jumps from the right to the left, by bilinearity, again, the product can come right in. So this is equal to that. And then this thing is literally the aggregate signature. Yeah, so you can also very easily verify these aggregates. And again, you can prove that this is all secure. Yeah, so again, very simple signature. Just using these bilinear maps already gives us properties that we simply didn't have before. And the last property I'll mention, and then I'll move on to more interesting things, is that it also supports very simple threshold signatures. So it's actually quite easy to take the signing key and break it up into essentially pieces, into like a bunch of pieces, such that each piece could be used individually to partially sign a message, and then all the partially signed messages could be combined into an actual signature. This is called threshold signatures. Very easy to do with this signature scheme. Again, this is something that we could do. The distribution properties are much better than what we had before. For RSA, we could thresholdize them, but it was hard to generate the keys distributively. For Schnorr, it was easy to generate the keys distributively, but it was hard to sign using these shares. And with bilinear maps, or with pairings, both key generation and signing can be done very easily in a distributed manner. And here, I'll mention a problem that's been bothering me for a long time, which is basically, can we have a threshold signature from lattices? And again, Chris has done some nice work in this area, but nothing as simple as what we can do with pairings or with RSA. So this is a really nice problem to solve. It's kind of annoying that we don't know how to do this yet. I don't see how to do it. I think we need to invent a new signature scheme for this. I don't think the GPV or any of the existing signature schemes from lattices we have will thresholdize. We need to invent a new signature scheme specifically with the purpose of thresholdizing it. And this would be a really nice problem to solve. It's kind of a missing piece in our puzzle, in that it's something that's trivial to do with pairings, and we have no idea how to get something as efficient with lattices. So this would be a good problem to work on. All right, so let's see. So I'm gonna skip over this next part here, and let's now move to multilinear maps. All right. So I showed you that already bilinear maps, which we know and love, they've really kind of transformed the world of crypto. We were able to build them from these, from pairings on elliptic curves. So all the work that the math community did on building pairings and showing how to compute them has been tremendously beneficial for crypto. But pairings, unfortunately, are not enough. Yeah, there are lots of things we'd like to do for which we need more than pairings. And so let me explain what these multilinear maps are. And I'll explain them in a way that I'll first kind of state the dream version of what we would really like to have. And then I'll tell you where we are and maybe how to get to what we would really like to have. So what is a multilinear map? So here, the structure is actually, I'm going to describe it quite abstractly. So the structure takes a little bit of focus to kind of understand what's happening here. So here we're going to have n groups. Yeah, so n is going to be some large number. So remember, before we had only 3 groups, G2, G3, and G6. Here we'll have a large number of groups. For each one, all these groups have prime order P, and they all have generators. Yeah, so each GI generates the appropriate group G sub I. And then we also have all sorts of pairings, which I'll explain in just a second. Now, what are the properties we want from these groups? So first of all, each of these groups should have an efficient group operation, just like before. They should all have, the discrete log problem should all be hard in all of these groups. And now the important thing to us is not so much the canonical representation which we had before. You remember from elliptic curves and in finite fields, we always had canonical representations. That's not so important here. What's really important is that the representation is short. And what I mean by that is that it's obviously allowed to depend on a security parameter, but it shouldn't depend on the number of groups dramatically. So it's only allowed to depend like the log on n as the log of n. And again, I'll explain that in more detail in just a minute. Okay, so far so good. So we have groups where representations are relatively short. And then we have lots and lots of these bilinear maps. So in other words, I can pair elements in GA and GB, and what will happen is I'll move to the group G sub A times B. Okay, and I want all these maps to be efficiently computable. So just to make sure you kind of have this structure in your mind, let me kind of show you a visual representation of what's happening here. Yeah, so let's say that the groups, let's look at the base groups as groups indexed by primes. So G2, this is just a way of keeping track of things. So G2, G3 up to G sub L, these are the first primes. The indices are all primes. And now what I can do is I can pair elements, and every time I pair elements together, I move to a group whose index is the product of the indices I started with. So right, I can pair G2 and G3, and I move to G6. I compare then G2 and G6 to G2 and G6, and I'll move to G12, and so on and so forth. Okay, so I have all these bilinear maps available to me, and I can pair however I want. And of course, at some point, I'm going to get to some largest possible value that's going to be, let's say, n is the number of groups I have. So eventually, I'll get to G sub n, and then I can't pair anymore. So far, so good. So again, we have all these groups. Discrete log is hard in all these groups, and yet we can do all these pairings to kind of move on from one group to another. If you like, the picture of the V pairing was really just the upper right corner here, just G2, G3, and G6. And what we're interested in is an algebraic structure that has much more structure to it. So we can do many, many more pairings than before. Now, why? Yeah, please, question. Well, so you have groups G1 to Gn. And you can keep on pairing as long as the index is less than n. Well, more than G2 to the n. You could get to G, well, there's an upper bound. There's a fixed upper bound. I call it n. And you can keep on pairing as long as the index you're in is lower than the fixed upper bound. Lower, just lower. Yeah, doesn't have to divide. Yes, exactly. So it's lots of pairings here. Yes, lots of pairing operations here. Does that make sense? So, well, again, the indices are just for bookkeeping purposes. So, well, so often people represent it using sets, but then you get the problem that you need to have like sets with multiplicities. So just numbers are a lot cleaner to think about. Yeah. So let me explain. So okay, so fine. So we take, so the structure itself, I imagine is clear, right? You compare G3 and G5 and you'll go to G15 and so on and so forth. When you generated the multilinear map to begin with, you pre-specified an upper limit, n. Now, if you are, for example, here at the very end, let's say that this number let's say this number actually is n. Then you cannot pair this group with anyone else, with any other group, because that's basically where your pairings end. It's what? Say that again? Yeah, you might never. Yeah, that's right. You might never use that. Yeah, absolutely. Yeah, exactly. You could pair G2 with itself, exactly, if you wanted to. So you could go to G2 to the n if you wanted to, or G2 to the L, G2 to the V if you wanted to. Yes, that's fine. Yes, but you can never go beyond n. So here, the condition here is again, the condition here is right. You can take any A and B as long as the product is less than n. That's the limiting condition. Exactly. Yeah, that's exactly right. Okay, so that's kind of the structure that we're looking for.
So you can have many ends to this thing. So if you pair G2 with itself many times, you could end up with some other group that has no connection to the G3.
Yeah, that's right. You could have another. You would have like you could end up with G1024 over here, and you might not be able to pair that with anything else. Yeah, that's fine. Perfectly fine. That's how you're going to generate these groups. Yeah, you're going to generate the structure in such a way that there will be a limit on how many times you can apply the pairing. Yes, that's exactly right. Yeah, and in fact, that's exactly what the constructions actually allow us to do. So, yeah.
I mean, I was more asking, like, this is somehow actually.
Well, yeah, this is what is being used in constructions.
My understanding is this is
Yes. Yeah, I wish we could build. We don't know how to build this just yet. Yeah. This is what we want. Yes. Right. Right. No, this didn't mean to be. This part didn't mean to be difficult to follow. So I just want to make sure. Well, I guess I've answered all. Is there any other questions on this? Yeah. What is arbitrage? Oh, that. The other way to do indexing. Let me just explain why this is kind of a natural way to index things. I mean, another way you could have imagined is literally we could have like groups G1 to GV, and now let's write G2 over here. Now when you pair these guys together, oh, thank you. Yes. I could have used indices G1, G2, G3 up to GV. And now when I pair G1 and G2, you could imagine going to a group that would be indexed by 1, 2. Yeah? And if I pair this guy, say I have G3 over here. If I pair these two together, I would move to a group that's indexed by 1, 2, 3. Yes, that would be another way that I could capture indices. Who was asking the question? Somebody was asking the question. But yeah. Yeah, right. So that would be another way to kind of keep track of these indices. The problem with this approach is that you see if I kind of pair, if all of a sudden now I want to pair G2 with G2, I get sets. So suppose I want to do, I want to pair GV by, so I want to pair GV with itself. I can't even write it. Yeah, so GV with itself. Now I have to kind of have sets that need to keep track of multiplicities of indices. And the minute you want to keep track of multiplicities, it's just easier to represent things using integers. And the notation actually works a lot more smoothly with integers. So that's why I prefer to use primes and products. It's just a way to keep track of what got paired with what. There's nothing fundamental about the primes and the indices. Yeah. Yeah. That's right. That's right. But again, the cutoff is an artificial value. That could be set to whatever you want. So you choose your application. You choose how many times you want to pair things with what, and that determines the cutoff. Yeah. Yeah, absolutely. Some you can pair more than with others, but that's fine. That doesn't matter. Yeah. The dream is actually not so much about this structure. This structure is kind of necessary. The dream is more about lengths. We really this is the dream. We really want to have these multilinear map structures where all the groups are small. The representations of the groups. They're all groups of order P, but the representations are small. That's the problem we're facing. That's just bookkeeping. That's just bookkeeping. That's just notation. Yeah. This is the problem. How do we come up with a structure like this where all the groups are small? Okay. So everybody with me so far? Okay, good. Yes. So now, so why do we call these things multilinear maps? Well, it kind of should be obvious to you. If we compose all these maps, so we have all these bilinear maps. If we compose them all together, then essentially we'll get one large map that acts on the base groups G1 to GL, mapping us to G sub the product. Okay. So.
Do you assume some associativity then? If I multiply 3 of them, then it makes a difference to
No, they would be associative.
Is that next to you?
No, they would be associative because these are all cyclic groups. Yeah, because they have prime orders, you have cyclic groups. Yeah, so associativity follows. Yeah. Yeah. All the groups are all exactly order P. Exactly. All same order. Yes. So this is why we call these things multilinear maps, because, well, they're kind of
If I take a generator of G2 and a generator of G3 and a generator of G5.
Yeah.
I pair the first two, then I get a generator of G6.
Yes.
And I pair it with G5, I get a generator of G30.
That's right.
So now I do it the other way around. I first pair the 3 with the 5, then
Yes.
I get a generator of G15, and then I pair this one with the 2, I get again a generator of G30. Why are those two the same?
That's a good question. They better be the same.
Yeah, but that doesn't follow from what you're saying.
That's actually, hold on. Actually, just let me just think about this for one second. So, actually, do we need them to be? No. It's a question of whether we actually need them to be. So that's actually a fair point. Do we need them to be associative or not? That's right. That's right.
So now we are in the 19th century.
Good. Thank you. Good. Very helpful. Very helpful. Thank you. Good. So at the end of the day, we want to multiply matrices, and I guess when we apply them in a fixed order anyhow. So it doesn't really matter. It's true, and we do want them to be.
And is the pairing G8 times GB the same as GB times G8?
No, that doesn't. I mean, the pairings are the domains could be different.
No, but if I pair G2 with G3,